Good day, everyone. It's evening here in Malaysia. Yes, welcome to this conference, inaugural conference. We have two speakers in this first half of the conference. And then the first one, perhaps I shall introduce to you just in case he gets disconnected. I won't speak too much. So we have Sukao here. He's our, currently he's with University of Nankai University in Tianjin, China. So he did his PhD in 1998 under Greg George. I'm not so sure if I pronounce his name correctly. Is it George?
Prof.
Yeah, thank you. At UCLA, and then he continued his postdoctoral at Caltech University. His main research interest is in descriptive set theory. So today's talk, he will be sharing with us the Herwig-Lascar property of groups. So off to you.
Thank you very much. Let me share my screen over here. And yes, so thank you very much for the invitation. And I want to congratulate to everyone in the newly established Logic Association of Malaysia. In China, the color to use for any celebration is red, and the image to use is the red lanterns. So I found this image over here to send my sincere congratulations to everyone there. And also thank you for the opportunity to talk over here. So the results in this talk are from some joint work with several people, including Mahmoud Etadadi Aliabadi, who's my postdoc at University of North Texas, and Francois Lemaitre and Julien Mallory, two French mathematicians in Paris. So I just joined Nankai University less than 2 months ago. So before that, I worked at the University of North Texas for 20 years. So this work was done while I was in the US. And so I'd like to go right into the subject over here. And as you can see from the top of the slides, my talk is going to be 3 parts. The first part is going to be some background, particularly the EPPA property and the Herwig-Lascar theorem, which is the motivation for the rest of the talk. And then I will talk about the Herwig-Lascar property of groups and some results over there. And in the third part, I will talk about some deeper results about the Herwig-Lascar property, which I for short HL property, and between the HL property and the structural extensions of logic. And so this is, in some sense, it's not really properly classified as descriptive set theory, but it's mostly model theory. But I think that I noted interestingly that yesterday when I did listen to Alex Wilkie's talk, and he talked about model theory and its connections with analytic number theory and the algebra. But he was interested mostly in the effectiveness and the computability aspects. And then when Yang Yue talked, he talked about the Ramsey theorem, which is used a lot in set theory as well. So I think that we are actually, now I'm talking a little bit about model theory. And so I think that in logic, everything is connected. So that I truly believe that all good mathematics are connected to each other. So let me talk about the subjects today, the property, the EPPA property. Let me first define it. So throughout this talk, I will fix a finite relational language L and consider L structures, mostly finite structures, but sometimes also infinite structures. So a partial isomorphism between two structures is a true isomorphism from one substructure of the first structure to the second structure. So over here, it is important to note that the partial isomorphism over here, from the point of view of these ambient structures, is a partial isomorphism, but it's actually between the two substructures over there, and also a partial automorphism of a single structure is therefore just an isomorphism between two substructures of the structure, and these two structures could be very different. So the picture over here is actually that if you have a structure C over here, there could be two totally unrelated substructure over there and an isomorphism between them, and we call this a partial automorphism. Okay, so the next concept, which is defined by Hrušovský in his seminal paper of 1992, is to talk about a class of L structures. So this class C is said to have the extension property for partial automorphisms. That's where the EPPA shorthand came from. If the following conditions hold, which is that whenever every time you have two structures, C1, C2, that satisfy that C1, the first one is a finite substructure of C2, and C2 is in general infinite. And also the property that every partial automorphism of C1, this finite structure, extends to an automorph, the true automorphism of C2. Then, so the picture is that there is a C2, which is in general a big structure, a infinite one, and a C1 is a finite structure, a substructure over here. A automorphism, partial automorphism of C1 can be lifted to a true automorphism of C2. So if this happens, then we can actually find a finite structure C3 to play the role of C2. So we can replace the C2 by a finite structure C3 that has the same property. C1 is a finite substructure of C3, and also that every partial automorphism of C1 extends to a true automorphism of C3. So this is very, very amazing, because the Hrušovský noted, of course, that the class of all graphs has this kind of property, which is we do know from old results of Erdős and others that there is this object called a random graph, which is a countable object that has all the finite graphs represented over there, and it has the property that every time you have two finite subgraphs of R that has an isomorphism between them, then that isomorphism can be extended to a true automorphism of R itself. So, but this R over here is an infinite structure. So what Hrušovský's phenomenal result was to say that this one, that you can actually find a finite structure that plays the role of this random graph. That's truly amazing. So at the time in 1992, he's the first one to define this EPPA property, and also he proved the first result about the class of all graphs. And as you can see that when we talk about EPPA, we actually care a lot about what happens to finite structures. So sometimes you see me talk about the class of finite certain structure has the EPPA. Over there, it goes without saying that there is an infinite structure that plays the role that's similar to a random graph. So, so now we come to year 2000, Herwig-Lascar, which is another seminal paper of the field. They proved this, once again, truly amazing theorem, but it's an extension of Hrušovský's result, which says the following. If you have a finite relational language L, and also you identify a certain finite set of finite L structures, and consider all the class of all T-free L structures. T-free L structures means that I put the definition below here. The T-free L structure means that there's no structure in the class T, which is a finite collection, and which allows a homomorphism from this class, from this structure T over here, sorry, to to our structure M. In other words, our M doesn't have pictures, copies of T in there. Okay, these are not true isomorphic copies; they are homomorphic copies of T. So, so Herwig-Lascar proved that the class of all T-free L structures have the EPPA, and so this in particular is a generalization of Hrušovský's result, because in Hrušovský's case there's no T. I mean, T is an empty set over there. As you can see, Hrušovský was interested in one particular class of structures, but Herwig-Lascar's theorem talks about really the abstract notion of L structures, albeit the relation in the relational language. So, but this is truly amazing. It brings this result properly into the realm of logic. Okay, and the EPPA has been studied a lot. It's firstly defined by Hrušovský, so some people call it the Hrušovský property. So if you see a paper mentioning Hrušovský property or EPPA, they mean the same thing. So the current status of the EPPA, it has been extended quite a bit. There are a lot of other people who wrote papers about it, and this is, in my opinion, is very well summarized in a very recent paper by Ribes-Zaleskiś, Konecny, and Nesetril. So their title is called "All Those EPPA Classes and Strengthenings of the Herwig-Lascar Theorem." So this is just a manifestation of the subject being very active. Okay, so from this EPPA, so this Herwig-Lascar theorem is the one that is motivating the concept that I'm going to talk about next, which I call the Herwig-Lascar property, but it's already defined in the original Herwig-Lascar paper. And the truly amazing thing, another truly amazing thing about Herwig-Lascar theorem is that they proved that logic theorem, to remind you that it's a theorem about L structures and the class of L structures, etc. They proved it by showing some properties about combinatorial properties about groups, and this is another amazing thing. So let me just define this the Herwig-Lascar property over here about groups. So this is already implicit in Herwig-Lascar paper in the 2000. So the definition goes as follows. It's a little complicated, so bear with me. Let G be a countable discrete group. So we will only care about countable discrete group. And then we have several subgroups of G. A lot of times we care only about the finally generated subgroups, but in this definition, we consider H1, Hn, which are subgroups of G. And then we call something a left system. A left system is a system of equations on H1, Hn is a finite set of equations with some variables, which we denote as x1 through xm, and the constants g1 through gl. G1 through gl constants are from the group G, such that all of the equations in the system is they are of the form either some x, some unknown, this x is a variable, right? So we try to solve this. It talks about the left coset of some hj over there being a particular, because gk is a constant, some kind of left coset. So this is saying that my x really should come from a certain coset, and the other kind of equations would be of the form that my xi and xr, so there are two variables over here, we need to find solutions for both of them, and they satisfy certain kind of equation, again, about the left cosets of Hj. So if you have a whole bunch of equations of this, then this is called the left system, okay? And the Herwig-Lascar property says the following: if for every finally generated, this time we could consider only finally generated H1 through Hn of G, and the left system of equations H1 through Hn, okay, imagine that we have a system. I'm not writing it out, but it has a whole bunch of equations over here. And then we say, if it does not have a solution in G, okay, then there exists the normal subgroups of finite index in G, so which correspond to the N1 correspond to H1, Nn correspond to Hn, such that the same left system, if you replace any occurrence of H by Nj, Hj, Nj, Hj, replace it, then the new system also does not have a solution. Okay, so this is a very, it's the first time that you see this definition, of course, it's complicated, but note that this is a purely algebraic condition, right? So it's about groups, it's about left cosets of groups. And so what's amazing was that in the Herwig-Lascar paper, they proved that the finally generated free groups have this property, have the HL property. Okay, and and the next thing is that they use this to prove that theorem about the extension of finite structures to bigger finite structures. And so that is truly amazing. So this is a purely algebraic statement. So let me just say in a few words about why, so what kind of connection they're making. So what they're making is this. So if we have a structure C1, which is finite structure, and our goal is to try to find a C3, which is an extension of C1. What we do is to consider all partial automorphism of C1 and put this partial automorphism into a big set P. So I'll just call this a set P. Collect in the set P all the partial automorphisms of C1, and consider the free group generated by P. This in general is going to be an infinite group, and there's what Herwig-Lascar proved that was that there is actually a subgroup H of not just the one subgroup but several. In fact, H1 through Hn, but we consider all the cosets over here by H1 and Hn, and then sort of union them up into a structure. They have this very clever way of defining a structure out of these purely algebraic objects, and to show that this is actually going to be a sort of a solution of that left system over there. And if it doesn't have a solution, that certain thing doesn't have a certain left system doesn't have a solution correspond to that this structure that they construct being a good, a desirable extension of the finite structure over there. But this structure in general is going to be infinite. So what they need to do is actually to improve it into a finite structure. And what they do is actually to use that Herwig-Lascar property to replace these H's by N1, H1, Nn, Hn. Remember that these are finite index normal subgroups. So after you do this, the structure over here becomes finite because these N's are finite index in FP. And so because this is a free group and finally generated free groups have the HL property, then they can actually go ahead and use this and to create that finite structure over there. So this is really, if you think about it, I mean, how did they ever think about this in the first place? I have no idea. It's a moment of ingenuity that can lead to this. But anyway, this is really what their main result. But remind you that this is a pure group theoretic property. Okay, so in their paper, they also explained how they give a little bit of a hint of how they thought about this. So here I'm going to deviate a little bit, a digression to a different property called the Ribes-Zaleskiś property, which is better known in the combinatorial group theories community. So a group G has the Ribes-Zaleskiś property, which I abbreviated as RZ property. If for any finally generated subgroups of H1 through Hn, and this part is kind of similar to the HL thing, then H1 times H2 times Hn, when you do the group multiplication, about this subgroups, when you multiply them up, it's a subset, not necessarily a subgroup. So this subset over here is closed in the so-called profinite topology. So I'm going to define this profinite topology here by saying that what is a closed in the profinite topology? If you have a set, it is closed in the profinite topology if and only if the following property holds. If you get any element G, if it's not in the set S, then there is a subgroup of normal subgroup of finite index, so that when you surround this G by all the elements of N, so take Gn over there, it still doesn't intersect S. So if G is outside S, then G times N, which is a very big group because N has finite index in G, still does not intersect S. So this is what's called the profinite topology. So the RZ property says that H1 through Hn, this group that we get is closed in this profinite topology, and therefore it has this described the property over here. So Ribes-Zaleskiś in 1993 proved that the finally generated free groups have the RZ property. So you can see the analog over here. So this also explains why Hrushevsky did not prove his original theorem in this fashion, because he proved his theorem in 92, and Ribes-Zaleskiś only proved their Ribes-Zaleskiś property for free groups in 93. And so what happened was that Herwig-Lascar really realized that the Ribes-Zaleskiś work is actually very relevant to Hrushevsky's work, and they make the connection successfully. So I want to make a comment of a very quick fact over here, that the HL property is a strengthening, is a proper strengthening of the RZ property that we just talked about. So if you remember, what the RZ property is to say that if you take a G that is not in a certain set that is supposed to be closed. Sorry, my pen is not doesn't work very well. So closed, and then there will be a finite subgroup of normal subgroup of finite index, so that the Gn intersection this set is still empty. So I think that this is actually so I think I actually wrote it slightly incorrectly over here, because what I wanted to say was that the first thing is that if you have if you have D in H1 through times H2 times Hn, this is equivalent to the left system. Here's the left system, Xn Hn equal to Gn. Xn minus 1, Hn minus 1 equal to Xn, Hn minus 1, etc. And the last thing is X2 H1 equal to H1, not having a solution, sorry. So not in here, it corresponds to not having a solution, okay? But then the Gn intersection, this set is equal to empty, correspond to this left system not having a solution. So you can see that this is actually exactly the format of the Herwig-Lascar. So So this was noted, in fact, by Herwig-Lascar that the RZ property is a special case of the Herwig-Lascar property. So you can see that this is actually a very strange thing, like in logic, that we had to somehow ended up talking about solving algebraic systems in groups. Okay. Anyway, the rest of the talk I won't have time to include this much detail, so I'll just talk about the what is known about these groups. So first, in 2001, Kuboy, who is also a French mathematician who works in Marseille, he proved that if gamma 1, gamma 2 are groups with the RZ property, then so is gamma 1 free product with gamma 2. So in other words, the RZ property is closed-ender free products. And also, it's not too hard to note that if you have two groups and the larger group is a finite index over the smaller group, then the two groups have the RZ property or not have the RZ property at the same time. So, so another result is that if gamma, we have gamma 1, gamma 2, these are finite groups, and then we take a amalgamated free product in gamma 1, gamma 2, of gamma 1, gamma 2, it in general becomes, it's possible then that the resulting group is a infinite group, then this group has the RZ property. So the reason I mentioned these properties is that we later on use this property to prove other theorems. And also it happens that these three properties about RZ was proved, the first one was proved by Kuboy, but the latter two lemmas are proved by my colleagues Mallory and Lametta. And so in 2019, so this slides over here, I'll just put everything over here. In 2019, Mahmoud and I noted that what has been said about the RZ property can also be said about the HL property. HL property is a much more complex, in some sense, property, but it also satisfies that this property itself is closed under taking free products. Okay. And also, HL property also has the nice property that if you have two groups which are a finite index of each other, then they have the HL property at the same time or not have the HL property at the same time. Okay, and the other one is also stated exactly the same as before, that gamma 1, gamma 2 are finite groups. Then you take a free amalgamated products of them, then they have the HL property. Okay, so everything about RZ property that has been proved can also be proved about the HL property. So the reason that we were interested in these closure properties is that we were able to prove recently, all four of us working together, to show this property that is actually of interest to descriptive set theorists. So let me state it. This one says, the theorem says that the automorphism group of any Hansen graph contains a dense locally finite subgroup that is isomorphic to Hall's group. So it has a lot of concepts over here. So let me explain why this theorem is of interest. First of all, a Hansen graph is defined by Seward Hansen. So it's the unique countable homogeneous graph that is Kn free. Kn is the n vertex complete group, complete graph. So if you have n vertex, vertices over here, then so what I just draw over here was a 4 K4, okay, and then if you have 5 vertices is K5, etc. Kn free means that reminds you there's no homomorphism from this graph to my graph. So Hansen graph is, in other words, having a lot of holes. It doesn't allow clicks, in particular, of n element clicks. Okay, so this graph has the property. Hansen graph has the property that it's Kn-free, and it contains all Kn-free finite graphs as induced subgraphs. So, so Hansen graph is kind of like a random graph. And in the case of K0, empty graph, then it is actually exactly the random graph. So it's a generalization of the random graph. And the Hansen graph is actually defined in the 70s, but in some sense, it's kind of hard to study. In particular, we're interested in the automorphism group of Hansen graph. So we know that the Hansen graph has a lot of automorphisms, and this automorphism group is big, but we don't know how to characterize that bigness. So some time ago, Anatoly Vershik made a sweeping conjecture to say that one way to characterize the bigness of an automorphism group or whatever group is to say that it contains a large group. So his way of saying it is to say that it contains a dense subgroup that is isomorphic to this known group, which is large. So this known group is called Hall's group. It's actually defined by Philip Hall in the 30s. So I denote it as H. This is really just a facade. Now we understand. Hall didn't know about it, and it wasn't known until the 50s, I think. Now we know that it's the facade limit of the class of all finite groups. So it's a very important object. In terms of groups, this is kind of the largest, the correct infinite group to study, which is, which is by itself locally finite, countable group. So it's, but at the same time, it's actually quite large. Okay, so our theorem verifies a conjecture of Vershik, which says that the automorphism group of this Hansen graph, or any Hansen graph, because you can replace this Kn where n is greater or equal to 3 by any, so there are infinite many Hansen graphs, and all of them, the automorphism group contains this big object called Hall's group. Okay. Okay. Anyway, this is to prove this, we actually use this HL property, and in fact, Su Yao was at the Florida when I first gave a talk about this object. And then we actually proved the same thing for many other groups, but for this particular group, we only know, for many other groups, we have several proofs, like 2 or 3. But for this object, the only proof that we know of goes through this HL property. So it's actually very curious that eventually we actually need to understand this much better. Anyway, so this is an application. In the rest of the time, I would like to talk about exactly, a little bit more detail, but I'm not going to go to either proofs or any other new concepts, but just to unravel the concept that I just talked about is already technical enough. So the general, I think my general philosophy is to say that the HL property is essentially equivalent to structures having extensions. So in Herwig-Lascar's original paper, they showed how HL property implies the structural extensions. Like to say, if you have the group has the HL property, then the structural extension, right? But what our new contribution is to say that, find ways to say that these structural extension properties are equivalent to HL property. So it's necessary that we consider HL property when we consider these structural extension problems. Okay, so this I think in some sense is a little bit surprising. How can a logic kind of property be equivalent to a purely group theoretic property? I think this probably is some object that Yang Yue and his colleagues can study in the future about 2 different subjects of having this equivalence. Okay. So anyway, I want to use the rest of the time to to talk about these equivalents. So the very first clue was once again proved in Kuboy's paper in 2001. So so once again, our strategy is to go back and look at RZ property and what happens over there, because RZ is a kind of a special case of HL. So we did find this very early paper by Kuboy, which he proved that a group has the RZ property if and only if, this is important, if and only if, in other words, he already established this kind of equivalence, okay? The following thing happens, which is a structural extension property. So for every n partition structure is a structure X which are partitioned into n pieces, okay? And these n pieces are really manifested by n many unary predicates, okay? 2, and this is Pn, okay? Every n partition structure and the action of G on X, in other words, if action G on X will have to respect the structure, then it is actually it must actually send things from any P to itself, okay? And the finite substructure of X, so a finite substructure over here looks like a piece, okay? There exists a finite extension Y of A. So this X itself, it could be infinite, but then there's a finite extension. Here's X and here's Y. And the action of G on Y, the action of G on A. Sorry, I shouldn't have drawn this Y inside X. I didn't mean that, because this Y could have nothing to do with X itself. So this is my A here, and you have this X. Then I can construct this Y, which is a finite structure, and extend A. So you can see that this already has the flavor of that structural extension that is studied by Hrushevsky. So this RZ property is already known to be equivalent to this. And then in 2001, Rosendahl, Christian Rosendahl proved another equivalence, which is very interesting to us. He proved that the G has the RZ property if and only if another thing happens. This other thing is this time not about general structures, but about metric spaces. So, but still it has the same flavor of the equivalence of the RZ property itself being equivalent to some kind of structural extension, only that structure is a metric structure. So here, what he says is that if you have an action by isometries on a metric space, he called it finally approximable, because it's a kind of a mouthful to say what it is, so he gave it a name. So what this is saying is exactly that if G acts by isometries on a metric space, so here is X, which is I draw it big because it's not meant to be infinite, okay? And so X is infinite, A is a small part of it, and is a subspace over there. A is finite, and X is infinite. Let me switch to my red pen again. And here's my group G, okay, acting on this. And also inside G, we also identify a finite subset F. Then this F also acts on this A, okay? And so what he says that in such a situation, then we can find a finite metric space Y. Once again, this Y might have nothing to do with X. And the action of G, the entire G acting on Y by isometries, and the rest of it is basically saying that, and embedding pi from A to Y, which is essentially saying that the action or new action of G on Y. That's what it says. And he called it an F embedded. So this is a very natural notion, although it's slightly more complicated to state, but it's a very, very natural notion. only the new element over here is to identify a finite subset of the group. And when we call it an F embedding, we meant that the embedding only applies to the group elements of F. Okay. So if you compare the Rosendal's result with Kuboi's result, you can see that they're very different, but the RZ, the same property, is actually equivalent to both. Okay. So our job then is to consider the HL property, and we for a while we wanted to prove a equivalence, and that is what we needed to prove that theorem about Hansen graph. Okay, so in 2019, Mahmoud and I actually proved this equivalence, accomplished this equivalence that we wanted, which is to say the following. I apologize for the complexity of this statement over here, but when I draw pictures, I hope that it will become a little bit more understandable. So first of all, we basically want to say that the HL property is actually equivalent to something that has to do with extending structures. So we have a finite relational language with unary relation symbols S1 through Sn. This, you can actually think about it as S1 through Sn, really providing a partition of the original structure. Okay, so it plays the same role as Kuboi's N partition structure. Okay, and then because Herwig-Lascar considers T-free L structures, here we also consider T-free L structures. T is a finite set of finite L structures, and then we let D be a T-free structure. So here's my D, okay? And such that S1 through Sn is a partition of the domain of D, okay? And then let C be a finite substructure of D. So here we just as before, we are not talking about the subset C now, and but it's finite, okay? And then we have a finite subset of the group G. This is actually the Rosendal thing. So if you have G, then you have a finite part, which is F, okay? And suppose G acts faithfully by isomorphisms on D. So G acts on D, and G acts transitively on each Si. So this is a technical condition to say that the G shifts elements of Si around. Okay, then there exists a finite T-free L structure. This time is, we call it D prime. But D prime is finite, I drew it too big, but it's finite, and then it has everything that we wanted, which is G acts
Oops.
I think it's the VPN.
Network.
Yeah.
Okay.
Let's give him a couple of minutes.
All right. We lost him again.
Yeah. Has to be the VPN in China.
Right, so yeah, so far so good, but hopefully he realized it and he doesn't continue talking and not realizing that. Oh.
Yep.
Right.
Let me see if I can tell him about it.
You got your message? Oh, you're muted.
Yeah, I mean, I've sent him the message. Hopefully.
He said he's restarting his computer.
Okay.
Oh, okay. So to the rest who are here, if you have any question, you can always post it first into the chat.
Mhm.
Yep.
Can you hear me now?
Oh, yes.
Okay, sorry that I think you have to reset my right to share screen.
All right, you're done.
Okay, thanks. All right, so I think this was the slide that I was talking about when I got dropped. So time is still good, so I promise I can finish it in time still. And so let me move on to the next topic over here. I just said that the HL property is equivalent to this very complicated structural extension thing. And then there's a third clause, which is unimportant looks, but in our proof is actually quite important, is to say that when we consider these finite set of structures, every one of them, in addition, we require it to be a so-called Geifman clique. This is actually, once again, a very strange property. I'll say what a Geifman clique is. A structure is called a Geifman clique if any two elements of the structure is related by certain relation. This is a very strange thing, I would say. Let me just try to draw a picture over here. So we have a wait. Okay, we have a structure and the 2 points, over there, and any 2 points is actually related by certain relation in the language. So this is actually what's called a Geifman clique, and not a very normal kind of property, but somehow strangely we need this. I want to mention that the condition of Ribes-Zaleskiś also around the same time proved something about this subject. Like, you know, it's actually quite similar to what our consideration is. I'll just therefore I feel like I should mention it. So they consider also the situation we have a finite relational language and a finite set of finite structures, each of which is a Geifman-Clique. Then they finally, in full generality, proved that the class of all finite T-free structures is a facet class with so-called free amalgamation property. This is quite important. And then they also proved that this so-called coherent EPPA, which is a strong strengthening of EPPA, and through that they were able to show that the automorphism group of its facet limit contains a dense locally finite subgroup. Okay, so compare this to our result, you see that they almost did what we did, that this facet limit contains a dense locally finite subgroup. And what we showed was that that dense locally finite subgroup can be isomorphic to the host group. Okay, so I think this is going to be my last slide. So what we showed in comparison was using that kind of equivalence and all of these properties about HL, the Herwig-Lascar property. I mentioned these closure properties under free products, finite index extension or subgroup, and the observation that the two finite groups, the amalgamated products between two finite groups is always satisfies the HL property. All of this is used in the proof of this theorem over here, and which is kind of an extension of Ribes-Zaleski's result. So let me just read it. We have a finite relational language, a finite set of finite structures, each of which is a Geifman-Clique. And then we consider the class of all pairs, M and G. So M is a structure, a T-free L structure. G is a finite group of automorphism, basically. G acts on M by isomorphism, okay? Then we basically prove what we proved truly as everything else is a corollary of this, is to say that this is a facet class. So what Ribes-Zaleskiś proved was without this G part, the M thing forms the facet class with the strong amalgamation property. So what we proved was this pair form a facet class. And then once we have this, when we take the facet limit of such a class, the group piece will give us the dense locally finite subgroup of the automorphism of the structure as a isomorphic copy of the host group. So this is what really happened. So that's why I want to mention this as a concluding theorem over here. So let me just, yeah, this is all my talk is about. Thank you very much.
Thank you so much. That was quite quick. We was about to give you some more minutes, actually, because we lost you. Yeah. We have a question. Maybe we can spend more time on the question and answer. There is one question by DC. It's written DC. And question 1, is the axiom of choice assumed in the work? And then the second question that follows by him as well, can any assumptions of AC be lifted, especially Tycho-Nov theorem?
So the AC question, okay, formally, yes, formally AC, so people working in this area never really cared about AC, or, you know, they were never careful about the use of AC, so they freely use it. So formally, this theorem was proved without actually really paying too much attention to its effectiveness. But I believe, because all of these theorems are really talking about countable objects, I believe AC is not really needed in this work. There's one piece over there that the whole thing is fairly constructive, because when we state a theorem that says that here's a finite structure, there's a finite extension of it, one would imagine that there is a sort of a computable way of taking one finite structure to another. But unfortunately, this proof over here is an existential proof that, just like I said, the construction of that finite index subgroup of a free group, that piece is not really computable, not really. So it's an existential proof over there. I forgot what the second question is. Can you repeat?
It says, I think the first one is the axiom of choice assumed in the work? And then can any assumptions of, I guess, AC is axiom of choice be lifted, especially in Tychonoff theorems? And then he replied as well. I mean, he continued texting, and he said that he's currently working on a axiom of choice for his project.
Okay. Yeah, certainly axiom of choice is equivalent to Tychonoff theorem, right? So yeah. So I yeah.
All right.
I don't have more comments about it. I think than the common knowledge. Yeah.
Right. So I hope DC, we've answered. Sugawa has answered to you. Any more questions? You can also perhaps unmute yourself and then just say your name and then your questions. We still have time.
Yes.
What is the prerequisite to look at things like this? I mean, to work on this topic.
Yeah, that's an interesting question. Like, when we actually look at this, we were amazed by the creativity of these authors, and so the kind of tools. It's truly very creative, right? What they considered over here. But on the other hand, I think that a lot of like even the RZ property, the Ribes-Zaleskiሥ property, is fairly new, and immediately after they consider the first out of consideration of some combinatorial group theory, but immediately got this notion was noted by logicians to be of use. So you can see that there are several logicians who immediately started to prove theorems about characterizing the RZ property using logic notions. So I would say, yeah, in general, there's not a single course that will prepare a student to really be ready for this. And I think if you talk about it, there are several things. There's in general, the group theory, the algebra, the group theory, that is actually needed. And then the other piece would be model theory. I think that because Khrushchevsky is a celebrated model theorist, and he first considered this as, I don't know what motivated him to consider this result, but it must be about the models that is actually that interest him. And interestingly, like I said, the descriptive set theorists, actually, we care about the automorphism groups, or the big groups, the Polish groups of these structures, because we believe that they are very beautiful objects, and there must be some very nice properties about them. And so that's how we came in. Yeah.
All right.
All right. Thank you.
Okay, thank you.
Any more questions? If not, If not, then shall we go to the next speaker then? All right. Thank you so much, Suga, for the excellent talk. I'm also learning something new that